Hello everyone, I'm Cheng, a postdoc at ETH Zurich. I'm happy to share a recent study from collaborations with Stanford University and IBM Research. The study is entitled RELIC, Investigating Large Language Model Responses Using Self-Consistency. Even though the text generated from large language models is fluent and looks convincing, it may include non-factual information. These inaccuracies are known as hallucinations. In this study, we aim to identify the inaccuracies and convey this information to large language model users to help them recognize these model mistakes. Self-consistency can be used to identify these inaccuracies. The idea is very simple. If the model responds differently to the same question, the model is not confident about the answers, and thus the model should not be trusted. When the question is in closed form and the model response is simple enough, we can directly compare the words included in the responses to justify the uncertainty. However, in practical usage scenarios, people ask the model open-ended questions. In such cases, self-consistency is hard to define and measure. Text containing totally different words can be semantically equal, and a subtle change in the text may completely change its meaning. Thus, it's hard to rely only on the superficial features, like how many words are matched between multiple responses, to determine self-consistency. Besides, when the text is complex and includes multiple claims, the self-consistency is hard to define. Using a score to convey self-consistency is less informative. We propose the following computational pipeline to tackle these issues. We use divide and conquer. Suppose that we are interested in verifying the correctness of the model's top response. We first use an effective prompt to break down the text into elementary claims. Each claim carries a single piece of information. We then use other responses to verify each claim separately to justify if the response logically entails the statement. The problem is well defined in the NLP field, which is known as natural language inference. Many existing methods and tools have been published and tested. We use an off-the-shelf language model, which is much smaller than ChatGPT model, to justify if the response logically entails the statement. Using this method, we iteratively verify all claims and get the number of supporting, neutral, and contradicting samples for each claim. Using the idea of atomic claims, we can go further. To make it more intuitive to users, we aim to find out the corresponding sentences and phrases in each response that directly support or contradict each claim. We use a question generation prompt to turn each claim into a question and use the question to find answers in other responses. Using this method, we can find comparable alternatives for each claim in other responses. Based on this computational pipeline, we propose RELIC, an interactive visualization system to help users verify large language model responses using self-consistency. We then introduce the system using a use case. When the user inputs a prompt, the system obtains multiple responses from the target language model and displays the top one in the response view. To provide users a clear understanding of the consistency of model responses, the system breaks down the top response into individual claims. Each claim conveys a single piece of information. User can select a sentence to look up the corresponding claims. The system verifies these claims with additional responses samples and presents the results in the claim view. The blue bar represents the number of samples that support this claim. The orange bar represents the contradicting samples, and the gray bar represents neutral samples, which do not contain such information. By clicking the bars, users can locate the supporting or contradicting sentences in other samples. The system uses the claims to identify keywords and mark the consistency of keyword alternatives from the other samples. In this example, the model response is very confident about Don Featherstone's nationality, year of death, indicating high confidence. On the contrary, the model is very uncertain regarding the person's education and other detailed information, which suggests such information is untrustworthy. Users can further explore the rest of keywords by hovering or clicking on them to gain more insights. For example, even though the model is not 100% confident that Don Featherstone was born in Leominster, we can notice that all alternatives are cities located in Massachusetts. Thus, the model may confirm this person's birthplace at the state level. Users can also click on the alternative options to locate corresponding sentences. To confirm the text that is not identified as keywords, users can turn on the marking mode and brush the text segment of interest. The system will then suggest a question to describe the selected information. Once the user confirms the question, the system will use it to search for answers in all samples and create a new keyword annotation based on the results. Finally, users can use the editor tool to steer the model generation based on the findings from the exploration. After removing the inconsistent information, users produce a more trustworthy biography from the model generation. We evaluated the system with 10 participants. The participants used the system to verify and correct large language model responses. According to their feedback and other lessons learned from this study, we summarize the following two design implications. Large language models enable people to interact with information using natural language in the most flexible way. However, it sometimes also makes the outcome unpredictable. Structured interactions can complement natural language-based interactions to help users take control when interacting with large language models. Second, large language models can be useful tools for analyzing themselves. However, using additional language models and prompts may bring new errors and biases. To minimize the risk, we should use these models to solve the elementary and well-defined tasks instead of open-ended problems. In summary, in this study, we use self-consistency to measure the language model's confidence, which implies the correctness of the generated text. In our method, self-consistency is measured using an off-the-shelf language model, where contradictions suggest the lack of consistency. For long-form text, we use divide and conquer by breaking them into atomic claims and evaluate each claim separately. We propose a visualization tool to convey the information of consistency to users and support them to identify and correct hallucinations. As a future extension, we expect to apply this method to verify large language model responses using information from additional sources and compare responses from multiple models. It helps model users combine multiple language models' responses to make better decisions and enable developers to compare the alignments between language models. And that's all for the presentation. You can find more information on our website. Thanks for listening.